Hi, I'm Lewis, CTO at Dataform. A couple of clarifications. When I'm talking about SQL, I'm talking about the language SQL, not SQL versus NoSQL. And I'm going to use some of these metaprogramming, metalanguage definitions a little loosely. Okay, so why did we do this? We want a scalable solution for managing data transformation processes that works for everybody working with that data, so our entire data team. We love SQL for this. It's growing in popularity thanks to modern cloud data warehouses. SQL scales extremely well. It's a common language for the whole team. It's probably the closest thing we're going to have something which everybody throughout the whole team can understand. It scales extremely well, and it's quite nice to develop with. When you develop SQL, you can run that query immediately. When we do a similar thing in code, we have to build and deploy and then find out that our code doesn't compile. But it does have some problems. So SQL primarily doesn't scale from a kind of organizational perspective without some additional tooling to help it do that. So fundamentally, the problem here is it's hard to adopt software engineering best practices when you're building SQL-based data pipelines. SQL isn't a programming language as such. Things like releases, version control, writing unit tests, or reusing code between queries is tricky to do with just pure SQL. So in order to understand how to fix these problems, let's dig a little bit into what exactly SQL is first. So SQL is a declarative query language. Declarative programming is when you say what you want, and imperative programming is when you say how to get what you want. So typically, if you're running some Python or some JavaScript, you're doing imperative programming. You're telling the computer how to manipulate the data in order to produce an output. In SQL, we don't really do that. We more tell it what we're trying to achieve. We want to sum these numbers. We want to group these numbers. And that's quite a fundamental difference. It's a limitation, but it also has many advantages. So looking at the advantages of being declarative, SQL queries can be parallelized as a result. Every data warehouse or SQL engine has some kind of query planner which can do fairly impressive optimizations. And it can also parallelize computations like a sum across thousands of machines. If you compare this to the kind of optimizations you can apply in an imperative programming language like C++ compiler, they're far more restricted in what they can do. They're usually quite localized and low-level optimizations. Additionally, SQL statements generally don't have any side effects. They can't call, when they execute, they can't call other APIs. They can't mutate state out of what they're actually doing. Obviously, you can delete and insert into tables. We also have a nice benefit that even though it is very possible to write a SQL query that will never terminate, and I'm sure many of you have, generally, theoretically, we know that it must terminate at some point. So there's a few exceptions to that. Generally, SQL is not a programming language. There's a few features that it falls short on. There's no iteration or recursion. You can't write a for loop in SQL. You can do some of the stuff with some SQL features like recursive CTEs or flavors of SQL like T-SQL, which allow you to actually introduce control flow, although we wouldn't necessarily recommend that you do that. So it's declarative and it's also static. It can't kind of mutate itself. Okay, so let's look at some code examples. This is a pretty simple SQL query. which takes a table and groups and sums by a age bucket. We can't reuse this code very easily. And there's a few reasons, but the main reason is that the input is fixed. I think we often think of a SQL query as a function, but it's not a very useful function because it has no parameters. We can't change the input to the function, and this causes us a lot of problems around code reuse. It's better to think of a SQL statement as a block of code, which is just going to execute. For the same reasons, we also have a problem writing testable code. This same query, if we wanted to actually write a unit test for it, would be very difficult to do because we couldn't pass in some mock data so that we could actually have a kind of self-contained unit test. And again, this is because there are no parameters here, there aren't any variables. It's just a block of code. So we need some kind of function or parameterized functions in order to be able to write tests. Okay, so another example, and we have a real use case for this ourselves, is we want to be able to write for loops and iterative code. I would love it if I could write some SQL like this, but sadly I can't. But we'll show you how you can do this in a bit. This is an example for dealing with GDPR data. We have a lot of tables containing user information, derived tables, which are transformations of our raw source tables. If somebody's wants to be removed, gives us a GDPR deletion request, you want to go and make sure that you remove that user from all of the relevant tables. In this case, there's just 3. There might be hundreds. You don't want to copy-paste the same delete statement into 100 different queries. So a for loop would be extremely useful here, but obviously this does not exist. Even if it did exist, there's no variables as well, so this would be kind of hard to accomplish. Okay, so how do we fix these problems? Metaprogramming. I copy-pasted all of this from Wikipedia. But in general, metaprogramming is a technique in which we can treat other programs as our data. We can also use this to move computation from runtime to compile time, which is kind of the same thing, and this is exactly what we're going to do with SQL in order to make it more expressive and to solve some of the problems we just looked at. We don't want to throw the baby out with the bathwater. We like SQL for a number of reasons. We think it's a great way to develop data transformation pipelines. We just need to fix it in a few ways so that we can apply software engineering best practices as we develop SQL so that this approach will actually scale as our team grows, as our company grows, and we're dealing with hundreds, maybe thousands of data sets. Okay, so let's look at an example of metaprogramming and how we can solve that fundamental problem of our SQL is just a block of code and it's not a function that we can parameterize and reuse. This is some kind of, JavaScript, but doesn't really matter. We have our original SQL query on the left. If we can wrap this up in a function which takes some input parameters and then generates us a query so that we can change the input, or we could change the, in this case, bucket size, then we can start to do some interesting things, and we can reuse this code in multiple queries, or we can write a unit test for this SQL. This is a fairly simple example, and I imagine that in this case, the query is simple enough that you would want to just rewrite it anyway. But there are some more complex situations, for example, dealing with complex operations, loading data in and out of Redshift, for example. These can get quite complex. There's maybe validation logic you want to add, or lots of parameters that you might be able to control. So this can become extremely useful. This is effectively a code generator. Our function is a code generator. it's going to generate us a SQL query, which we can then go and execute. This is the pretty key step in everything we're going to do and all of the fixes we're going to apply and how metaprogramming really helps us solve these problems. So we want code reuse. We want some imperative, iterative, recursive programming. We're going to want to introduce some basic control flow, some if statements, only run this statement if this other statement fails or passes. We also want to maintain some of the benefits of SQL as a declarative query language, and particularly at runtime. Something that we would like to avoid is arbitrary imperative user code executing at runtime. And as you'll see in a second, our solution here is to push a lot of that into a compilation step. Okay, so Dataform is an open source framework for managing your SQL. We have a we can think of it like a metalanguage and a compilation step to produce SQL-based graphs of actions that we want to perform against our warehouse. And we have a number of abstractions inside the framework, which makes it easy to develop. Currently, we support BigQuery, Redshift, Postgres, Azure data warehouses, a few others on the horizon, Presto, Athena. The entire framework's written in TypeScript. It's open source. You can check it out, and I'll put some links at the end of the talk. Okay, so the framework overview. We want to make it easy to write parameterized SQL. We want to make it easy for you to define directed acyclic graphs. I imagine any data processing tools you use some notion of DAG, the data flow model. It makes a lot of sense for data pipelines, and we're not doing anything different here. There's a few other features and abstractions that we're going to add in as well. So a thing that comes up a lot for us is testing. We are going to look at some unit tests, but also runtime assertions. So if your data pipeline produces some invalid data, either in a staging or production environment, you want to be able to detect that, and you want to be able to either alert somebody, or maybe you want to halt the pipeline. We have first-class support for unit tests and a number of other things that we know are quite important to building a scalable data stack, such as being able to write documentation, managing environments and different releases. So this is our approach to solving many of those problems with SQL by introducing this compilation step. We think of it a lot like how you would compile another programming language, like C. We have a number of different phases, and they're all there for very good reasons. So on the far left here, this is what you would effectively call the language. We have a JavaScript API in which you can do pretty much anything. We also have a SQLX format, which is a kind of a mashup where you can primarily write pure SQL, but provide JavaScript-based templating and configuration blocks for you to provide metadata about the query that you're developing. You're allowed to write imperative code here. You can write for loops and all of that good stuff to build out your graph, so we can solve some of those problems we saw before. It's also a sandboxed environment. I have a slide on this, so I'll skip it for now, but it's quite an important thing that we added to the framework. You don't want, typically when you compile any other language, you don't have the ability to make network requests or read the file system at compilation time. One of the reasons this would be bad is because you want compilation to be extremely quick. A lot of these design decisions allowed us to keep compilation of even very large Dataform projects to under a second, and that has a lot of benefits for developing. Otherwise, you could spend a lot of time waiting for us to do things. There's a The output of the compilation process is a compiled graph. I mentioned before that we want to keep some of the advantages of having a declarative static query language, which SQL is. And the compiled graph, in our case, is static and fully declarative. It's a mixture of actual pure SQL and in a JSON object, which you can kind of inspect and work with directly if you want to. Once we have a compiled graph, which kind of tells us everything, every operation or action inside our data warehouse, we then need to go through a final step, which we call build, which is, I guess, similar to a normal software kind of build process. In the build step, we actually introduce information from your data warehouse. So information such as what tables exist. And we use this to generate the final SQL statements that will actually get executed. So this can take a bit longer because we need to make network requests. But as a user, this is generally hidden from you. You don't have to worry too much about it. And you're just worrying about the compilation process. OK. So this is an example of a Dataform operation or action that's done in two different ways. So I mentioned we have both JavaScript and a SQLX format. On the left, we are looking to publish a table. It's a very simple publish operation. We want to create a new table in our data warehouse, and we want it to just be a pure copy of the users table. On the right, we have a SQLX version of exactly the same thing. And in this case, you're primarily writing SQL, but you have additional language features to define some of the properties that you would otherwise do via the JavaScript API. If your team's used to writing SQL, this is usually where we recommend most people start. And for some of the more advanced use cases with the JavaScript API, you can do slightly more interesting things. So Dataform's abstracting some of these ideas, some of these common operations away. Given that the primary problem we're solving here is about building and managing a nice, clean, consistent set of data in your warehouse, publishing new tables and new views of that data is probably the thing that we do the most. Okay. This is a kind of example of how that code gets turned into a compile graph. So this is just a piece of JSON describing this action. We've got a name. We've got the table that we're going to create. We've got the pure SQL, the select star statement, and the type of the table that we want to create. So two things have happened during this compilation process, which are worth pointing out. In both of these examples, we have a piece of JavaScript in there where we're calling a function called ref and passing it in a string. In this case, we're aiming to reference another table that we've created as part of our Dataform project. When we compile this code, we end up with that reference function being expanded into a full table reference that we can actually, which is just pure SQL. We've also added the table that we depended upon to a list of dependencies and into some metadata about that action. This is what allows us to build up the directed graph and make sure that we can execute operations in the correct order. There's no create table statement at this point. This is still just a select query. We're generally, when you want to build a table, the primary thing you want to think about is writing that query, and the boilerplate around that isn't something you necessarily have to worry about. In certain warehouses, this is simple. We just append something like create or replace. In other warehouses, this can get a bit more complex. So sometimes you need to deal with temporary tables and transactions, and as users, you don't really want to have to think about that. So this gets kind of packaged up in an abstraction. So we can take our compile graph, and we can run the project, and we can do this all via the command line interface. The build steps run during that process, And this will, at first, describe all of the actions that are going to run when we run compile. And we can get the JSON out from that if we want to. And then when we actually run, we will go and execute the full statements, create table statements in your warehouse. OK, so it's basically a SQL compiler. We take your user code, we take your SQLX files, JavaScript, and we generate this kind of runtime format, which is the compiled graph, so that we can then execute those actions in your warehouse. We can write any code we want during compilation phase, but at runtime, the actions that we perform are fully declarative and static. They can't change dynamically at any point. There are a lot of benefits to this. It makes it a lot easier for us to reason about our data pipelines. We know that they're going to terminate eventually. It means we can do things like validation at the point of compilation and raise warnings very quickly. It's unlikely that you're going to get in a situation where you try and run your thing, and after an hour of execution, some user code throws an exception and the whole pipeline falls down. We can be confident that that's not the case because we've pushed all of those operations into a pre-compilation step. There are some control structures that we keep at runtime. I think the key thing here is they're not iterative. You can't do loops or anything like that. You've basically got the equivalent of if statements. You can decide whether to run something else if something passes. This is the only control structure we provide. It's somewhat opinionated, but it does mean that as these pipelines scale, and perhaps you have a number of people developing them or contributing to them who aren't software engineers or aren't able to reason about what's sensible to do at this stage, this kind of makes sure that no situations like that ever really arise. So one thing we want from our compilation step, and again, we would want this if we were compiling any other language, is we want it to be reproducible. If we have the same input, the same set of files on disk, and we compile the project, we should get the same output. That's one of the reasons why we sandbox the compilation stage and the user code, and it can't make any external API calls. You also have to be a bit careful yourself. You don't want to use non-deterministic code in this step, ideally. In most compilers, this would be impossible, but because we're allowing you to write arbitrary JavaScript, you could do this. So you do still have to be a little bit careful. OK. So that's our high-level solution to the problem. And then let's have a look at some of the use cases and real-world use cases that this actually helps us solve, and some code samples of how this looks. For loops. We can now write for loops. We can take our GDPR example from the past, and we can just actually write this in JavaScript. We can define a set of actions which will clean up certain tables. We can define the query. In this situation, the query is a Lambda function. We have a context for that query, and we can call certain methods on that context. This allows us to do the templating and parameterization that we wanted to do. All of this gets expanded into actual final SQL and a static set of SQL queries during the compilation phase. So this for loop no longer exists after we've compiled the project. So unit testing. SQL unit testing, I don't think that's a thing, but it is now a thing. And in order to do this, we needed, again, those parameterized queries. Going back to our age distribution example before, we can write that exact code. We can define a function. We can have a parameter for the input. We can use this to actually publish a table. We obviously do want to do this transformation or aggregation. So there's an example of that code below. But in Dataform, we can also write a test. So we can use our SQL query generating function. We can pass it in some mock data. In this case, I've just written a unional select statement. You can do this programmatically as well. And we can tell Dataform what we expect the output to be. So we mock the input, we define the output that we expect. And this is a self-contained SQL query. It doesn't have any dependencies on other tables. We still need to run it in our warehouse for a few reasons. Firstly, every warehouse is a little bit different. Secondly, it's hard to write a SQL query which actually checks for pure equality between two tables. These can all be run in parallel, so all of the tests that you define in a Dataform project can be executed at the same time because they are self-contained and don't interact with each other. Okay, so another cool example. If you're dealing with multiple environments, you have a production environment, you have a staging environment. Sometimes these production environments process a lot of data and can get extremely slow. It's not uncommon to see pipelines which take 6 or 12 hours, and you probably don't want to be running that in a staging environment because it's going to take you a long time to work out if you've broken something. So you can sample data in a staging environment. Again, because our SQL queries are parameterized, we can actually do that and generate different SQL based on the parameters passed into the compilation. So this is a little bit different because our SQL query is not a function, but we're accessing kind of global states at this point, or properties of parameters passed into the compiler in order to do this. This also isn't a great example of a SQL query because we're using RAND, so it's not entirely reproducible. But you could write this in another way. So I mentioned this before, loading data from S3. To do that in Redshift, there are a number of operations that we need to create, and I've shown some of them on the right here. But in practice, our actual libraries to do this need to do a lot more. We define temp tables, we create them, we rename tables and swap them out. So on the left, we have a function that we can call to actually generate all of the SQL for us, which means if we have a lot of data sets that we want to load in from S3, we can do it in a consistent way and we don't have to rewrite the same queries over and over again. This also means we can add in things like validation into our APIs. If we want to enforce consistency between the ways in which people load data from S3, then we can actually do that in our compilation step and throw errors which will be surfaced if they've been used incorrectly. This also allows us to redefine the APIs that we're using. So obviously there is a way to do a copy command in Redshift, and it has some parameters you can pass, but these can be wrapped up for your own use cases. Cool. Okay, so I've talked a lot about the framework and how we designed it. We also have a web platform, Dataform Web, which is a IDE for Dataform projects. So a new language is great, but without an IDE, it can be frustrating and slow to develop against. And this is actually really one of the biggest drivers to us building this framework, and specifically to us building it in the way that we did. We know ourselves that we're a lot more productive when we have a good development environment to work in, and we wanted to be able to provide the same for people working with our framework. Development speed matters. That's one of the advantages of SQL, that there's a very fast turnaround time to develop, test, and actually execute a SQL query. We want to be able to give that to the entire team. So let's have a look. So the IDE for Dataform projects, it compiles your SQL project in real time, similar to other IDEs do. You get warnings if you make errors or break validation rules. You can execute arbitrary SQL and preview the results. The web IDE also integrates with Git, so if, particularly if you have people in your data team who are less comfortable with the command line, you can use the Git integration to manage pull requests and create commits, manage merge conflicts, all this kinds of stuff. There's also everything else you'd expect from a web-based platform for data pipelines, scheduling, orchestration. We mentioned some of the documentation features of the open source framework, and there is also a data catalog built in. So this is the IDE. It's built around Monaco, which is an open source version of VS Code. We have our main SQL in the center, which is a SQLX file. We compile everything in real time, and it's visible on the right, so we can see the full compiled query. We can see if the query validated against the warehouse. We can see the dependencies that we've introduced, the type of table that's going to be created, and we can preview the results. And at the top, you can see some of the kind of Git integration features and a list of files on the left. So one of the benefits of this as well is we can build up a dependency graph during compilation, and we can visualize that. So you can visualize the dependencies between all of these different actions. This is an example, I think, from our actual internal Dataform project. These graphs can get pretty big, but the visualization is extremely useful to trying to understand how everything's interacting, particularly when you might be writing JavaScript and auto-generating a lot of these actions. This is enabled by the framework design and the fact that we do have this static compile graph that we can then visualize after the compilation step. So finally, there's a catalog as well. On the left here, we've got an example of how you can document a data set and provide descriptions to fields and the table itself. And this is useful if data governance is an issue, or if you have so many tables that you need to be able to share this with everyone on the team. Cool. So thank you. There's a few links here for the framework, for our doc site. I put examples from this talk of the actual code snippets in a repo, so you can check that out and compile and play around with that. We also have the Web IDE, which is free to try or free to use for individuals. And there's some good example projects on there that you can click around and play around with to get an idea of what exactly the Dataform Web looks like. Cool.
I want to ask you, somebody is bound to take this and use with untrusted data. So what about SQL injection? How do you guard against it? Because you cannot translate everything into SQL query parameters, because your parameters are not like SQL query parameters, like from clause and etc.
Do you mean SQL injection is in terms of like a security concern?
Yes, yes. Yeah,
so ultimately this is, when you're using Dataform, this is your project and your developers writing that code. Because of this compilation process is kind of sandbox, like nothing can really get injected in. Given that you have parameterized these SQL queries, yeah, you could inject, I guess, bad things in this case, but the only people who could write that code would be developers on your team. So I guess it's the same way, it's probably the same risk in that the developers on your team are writing code. They could mess everything up if they wanted to. There's no external threat from parameterizing these SQL functions.
Nice talk. I'd like to know, why did you choose JavaScript over Python, like GBT, for example?
Yeah, good question. So obviously, Python is the go-to language if you're developing data pipelines. So there are a few reasons here. I think one of the reasons here was around speed. We really wanted to keep that compilation time down and make sure it's very fast. I think possibly a bigger reason for us was sandboxing. The compilation process is happening in a sandbox, and we can do that in JavaScript. This is actually really annoyingly hard to do with Python. We'd also had some, so one thing I should say is actually when we developed Dataform, we'd actually started out building an IDE for DBT projects. And that's how the project actually started, that we wanted to solve that development kind of process and speed up the development process. So we kind of moved away from DBT for a few reasons, but yeah, sandboxing, speed, we wanted to just make sure that everything was extremely fast. I think, yeah, there was also some other minor practical reasons, like our whole stack and web front end and the IDE itself is all in TypeScript, and having a unified language across the whole stack there is nice. There's less of a reason to use Python as a language, given that we're never actually processing data, so that value is kind of lost. We're just generating these SQL strings. However, it is a new language to some people, particularly if you have worked with data, but it's relatively easy to get started and kind of growing in popularity.
Hey, thank you. So quick question. Around, like, I totally see how being able to parameterize all of your SQL queries and stuff could really help with the development process. But curious to see what tools you provide to help with like debugging, because I'm sure, let's say you have an error in one of your downstream tables and you want to debug what the source of that error is. It's a lot easier to be able to, at least for me anyway, it's a lot easier to be able to read SQL and to see how the data flowed from one table to the next rather than reading code.
Yep.
Where things aren't compiled yet. So, what tools are there for that?
Yeah, so after compilation, you have this massive JSON object with all of the pure SQL that's generated by the code. And in the IDE as well, I think we showed it. When you're developing that code and possibly writing for loops or functions, on the right we'll show you a kind of real version of the pure compiled SQL that will execute. So you can actually see the actual pure SQL that's going to run. And when we show you run logs, we give you a list of every exact SQL statement that was executed. So when your pipeline fails, you go have a look and you can see the actual pure SQL statement that ran and the error that was caused. So yeah, there are some efforts to make debugging easier. And I think in general, the IDE experience, the goal here was to not abstract away SQL too much. We still want to give you visibility into what's actually going to execute.
Cool. So the IDE can show you like logs and historical data, or like historical runs and things like that. It's not just for development.
Yeah. So I've mainly showed the development pieces, but the run logs, the orchestrator, will show you the pure SQL that was executed.